Okay, there is some other types of content that we've covered. We just breezed through those. Now go all the way back to page 77. So what I mean by that is we talked about atomic numbers. We only made a quick reference to what isotopes were. So what is a mass number then? Yeah, how many protons and neutrons? Okay, so we talked about that. So then, in short, that puts us up to page 82 at the bottom and where we want to begin. Okay, the relative atomic mass scale, okay, makes it possible to know how many atoms of an element are present in a sample of the element with measurable mass. The three very important concepts, the mole, Avogadro's number, and molar mass, provide the basis for relating masses in grams to numbers of atoms. That's why, yes, what did we talk about yesterday? That's why we said put molar mass down on there, because that is really what we had discussed. So, the mole. The mole is the SI unit for amount of a substance. Is all it is. It's just a counting unit, okay? A mole, abbreviated mole, is the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. The mole is a counting unit, and we talked about like dozens of eggs, where it says, okay, it's just like a dozen. We usually order 12 or 24 ears of corn. Oh, excuse me, we don't usually order 12 or 24 ears of corn. We'll order 1 or 2 dozen. Similarly, a chemist will want 1 mole of carbon, 2 moles of iron, 2.567 moles of calcium. In this section that follow, in the section that follow, it shouldn't say follows. Yeah, oh. You will see how the mole relates to masses of atoms and compounds. Have you ever done scientific notation yet?
Yeah, like the multiply.
Yeah. Okay. So, for the most part, you're probably going to want to get your calculator out. I am hoping, and it doesn't matter if everyone probably has a standard like this or like this blue one. Okay? I think that one will be fine. I'm familiar with that scientific notation. Okay, a lot of you are having the same type of calculator as myself. Okay. Okay, with this one, it might take a little bit of getting used to. It's got to be a secondary function on here, and I think it's that. It's not a secondary function, it's exp. And that probably stands for exponent, and that's what that's on there for. Okay. So, Avogadro's number. The number of particles in a mole has been experimentally determined in a number of ways. The best modern value is 6.022, and we don't go any further than that. We don't put the 1415 on there. So times 10 to the 23rd. This means that exactly 12 grams of carbon contains 6.022 times 10 to the 23rd carbon 12 atoms. The number of particles in a mole is known as Avogadro's number, named after the 19th century Italian scientist Amedeo Avogadro, whose ideas were critical in explaining the relationship between mass numbers of atoms. Avogadro's number is the number of particles in exactly 1 mole of a pure substance. For most purposes, Avogadro's number is rounded to what you can see there, like we just said, times 10 to the 23rd atoms. To get a sense of how large Avogadro's number is, consider the following. If every person, well, we're not going to go into that. Can anyone see the significance of using scientific notation? In other words, the calculations that we will be doing when we look at this it's a lot more convenient doing this as opposed to, okay, so 1, 2, 3.
Yeah. Oh no.
Okay, we now have the same numbers on here, these two. That means the exact same thing, okay? Does anyone think they know how you, I would be surprised, well, I'd be impressed but not surprised that you may not know how to convert scientific notation. In other words, if you see a number, how do you convert that to scientific notation? If you see a whole number, or excuse me, or if you see the scientific notation, how do you convert it to this? Or if you have a whole number like this, how do you convert it backwards to scientific notation? Are we familiar with that? Okay?
Is there 23 zeros or is it 24?
Neither.
No, you move the decimal 23 times.
That's exactly what you do. Okay? So this is what we mean. Would you want to see a number converted into scientific notation or a scientific notation converted into a number? Okay? So scientific notation converted to a number. Okay? At least that's, am I interpreting that correct? You said the second one, and that's, I think, what we have as an option. Okay, so let's see here. We'll go ahead and say, okay, so there is scientific notation. And one of the things that determines how we move that is the exponent a positive or a negative value. Okay? So what that means, you got a 50-50 chance. Are we moving that decimal to the left or to the right? Okay? So that means here is 2. Okay? So how many zeros do we put on there? Put 4 zeros on there. Okay? So that would be correct. So what might happen if this is a negative value?
Then you move the decimal 6 ways to the left.
Okay? Now, just by habit, this is how I choose to do things. It doesn't mean that you have to. You may choose to just start with the decimal point like this and then put your value in there. This is just a habit that I have. I always put a 0 in front. Okay? So if this is a positive exponent, we're going to the right. If it's a negative exponent, we're going to where? Going to the left. So if we move it to the left 1 spot, there's 1. There's 5 more remaining spots. So how many zeros would that be? That would be 5. Okay? So we have 2 numbers now that are the same. One has a positive exponent, one has a negative. Okay? Front row, are we on the bus here? Middle row, back row. Okay? Then you might be asking, well, what happens if you have this type of a number and convert it backwards? Well, good question. Okay, well, let's try something like, we'll do, okay, so now we're going just the opposite. Okay. Okay? When you do these, it has to be a number between 1 and 10. So what that means is we're going to the right 2 spots, okay? Because we're not going to stop here. That's not between 1 and 10. We're not going over to here. That's not between 1 and 10. Here you'd have 0.3. Here you'd have 34. So that's why it has to land right in that spot. Okay? So we're going to the right 2 times. Okay? So we know we're going to have 3.41. But this is the tricky part. If we're starting with a value that's already less than 1, it's going to be a negative value. So how many times did we go to the right? Okay? So don't always associate a positive number always going to the right. Okay? Or that a negative number only goes to the left. Okay? It's where this is, if it's going to be between 1 and 10. So it has to go in between there. And if the value has started to be a positive or a negative integer. Okay? If you can follow that, you'll probably be just fine. Because we can say just the opposite, again, is if we had something like, let me do this color. Maybe we've got, I don't want that number. Okay, so we're going to convert that to a number like this out of scientific notation. So this is what we're talking about. This was a negative exponent. In what direction did we move?
Right.
Right. So don't ever do it. Just say correct. Okay. Otherwise, no, you're right when you say that. When you reaffirm that, because sometimes you might get right and left confused. So correct. Okay. Because if you look at this, you say, oh, well, that's a negative exponent. Here, we went to the right twice. You would not do that here. For one reason, because this number is greater than 1. So when that happens, what we're going to do is we're going to have to move to the left, and how many zeros would that be? We've got 0 point, okay? Only need 1 0 to that. So that's a way of visualizing. You need to determine, is the number between 1 and 10, and is the exponent positive or negative? Confusion? Front row, we're on the bus here. Next row. And then back row. Could you repeat that again?
Like having like 4,000.
Oh, 4,000? Okay. So we'll do 6,120. I don't know. Just sounds like a good number. 6,120. Okay? So would this have a positive or a negative exponent, do you think? It's going to have a positive exponent. Okay? So the next thing we need to decipher is, what was I going to say? How do we get that? That's what I meant. How do we get this to a number between 1 and 10?
6.12.
So it would be 6.12.
Be 6.12 to the power of 3.
So since we're moving to the left, it must be to the negative third. No, that is not correct because this number is already greater than 1 or 10 or whichever way you want to look at it. So it's not to the negative third, it's to the positive third. All right? Now, one of the next things we want to talk about, so can we erase this? Okay. Because you will obviously be using scientific notation in this section because we read about it. We wouldn't be talking about it if it was not going to be utilized. So distance or mass, you pick. Probably mass. We'll do mass. Okay? So what we mean by that is if we have a gram here in the middle, okay, we move our measurements by powers of 10, whether it's positive or negative. Okay? If you were to take an ibuprofen or maybe some acetaminophen like we talked about or Tylenol, how are you measuring each caplet or pill? No. I don't think it would be, the ingredients into it might be micrograms, but the pill itself would not be micrograms. Milligrams.
Oh, I knew that.
Okay? Isn't that what you said?
Every day.
Okay. So what that means then, we've got decigrams here. We've got centigrams here. And then like you had just illustrated, we've got milligrams out here on the end. Okay? So then what we see happening here is now we're going this direction where we have, I always like to do it like this, a capital D, what's called a decagram. This is a decigram, this is a decagram. Then we have what's called a hectogram, and not a megagram. It's what you would see on your dumbbell weights. It's either this many pounds or this many what?
Kilograms.
This many kilograms.
Do you think it's a good idea to write these down?
I don't know. Depends what your understanding of this is. Because if you understand this now, you're probably going to understand it the next day. You're probably going to understand it the next.
So if I like saw those on the board and I'd be like, okay, I know what that is. I shouldn't need to write it down.
Sure. Okay. The reason we say that is, okay, you want to start in the middle and work to the outside, or start to the outside and work to the middle? Start from the middle, okay? So if we had 820 grams, okay? How many kilograms would that be? So I'm just going to pause this for just a moment. Remember, these move by powers of 10, and I'll have a visual aid for you here in just a moment. So I have your visual aid here. It's not quite up to scale like I was mentioning. Okay. In this hand, we have a kilogram. Okay. And then ideally, what this is supposed to be was a gram. I think it's a little bigger than a gram, and I can't read it on there because it's been corroded. And we can certainly see this would say stamped in there. It says 1 what? 1 kilogram. Okay? So when we look and apply this on this scale here, here's our kilogram, here's our gram right here. So just by looking at it by size, this is obviously a lot bigger. Okay? So what that means is it's going to take a lot more of these to make up 1 kilogram. Okay? So if we use that logic, is this going to be a bigger numeric value with zeros behind it, or is it going to be a smaller value with a decimal point? You are correct. Okay? So what this means then is we are moving that value to the left. How many times would you guess?
Twice.
How many times would you guess?
3 times.
3 times.
Okay? Because we're going to move it to the decagram, the hectogram, and the kilogram. So a decagram would be 10 times, just like a decade. A hectogram would be 100 times bigger because that's a century. Okay? And then a kilogram, as we would guess, is 1,000 times bigger. So with that being said, if we're converting this to a kilogram, there's one of two ways you can visualize this. That's why I didn't know how to answer your question in the back. If you can visualize this, do you need to write it down? Well, maybe, maybe not. But if you understand it today, you're going to understand it tomorrow. Because this has something to do with what we call dimensional analysis as well. So what this means is when numbers are next to each other, we multiply. We're on the bottom, they divide. So what we see happening here, we already know that you are moving this to the left 3 times, correct? Because again, this is 1,000 times bigger than this. Okay? So we want to cancel these factors out. This is our two choices. We either have this on top or we've got this on top. But if we want to cancel this gram, would we put a gram here or a gram below? Because if you put it below, because if you put it on the right, then you are squaring that value. We don't want to square that. We want to divide by that. And by doing that, the factors will now cancel. Okay? So how we look at that is here we've got, okay, we've got 1 gram, and we can put our kilograms here. Oops, because that's what we're looking for, because we're moving it to the left 3 times. And again, how many times larger is this than this? 1,000 times. So the reason that that's significant is if it's 1,000 times bigger, this is than that, what do we get when we divide those two?
What do you mean?
8,
0.8.
0.8.
If you divide 820 by 1,000, you get 0.829. Where did the 9 come from? Okay, equals what? No. No, you can put. I would put a 0 on the end, but that's just me. I guess that's 2 non-zero digits. We can just leave it like that. So how we're looking at this is one of two ways. Again, if you're here, we moved it to the left 1, 2, 3 times. So if we do it in dimensional analysis factors, 1, 2, 3. Because remember, everything on here is by a power of 10. Okay. Front row, we're on the bus here. Middle row, back row. Okay. So then just the opposite can take place if, okay, about 20, 26 after. Oh, we got time. Well, what happens if we have 4.60 kilograms? We want that to be in grams. Oh, I didn't label this, did I? Okay, so how many grams would that be? You don't necessarily have to do this if you understand that. So we're starting way out here at the kilogram. In what direction are we moving? And every jump that you make is by a power of what? Okay? So with that being said, you could probably throw out an answer right away. Well, yes. But what would-
460 grams. I meant 4,060.
4,600, yes. Okay? So, in case if some of you are wondering, well, how did you get 4,600? Okay? Well, how many grams are in a kilogram? Remember? How many grams are in a kilogram? There's 1,000. Okay? So for every 1,000 grams, you get a kilogram. You can put a 1 in front if you wanted to, but you don't have to. So here, the kilograms cancel. You're just left with grams. These numbers are next to each other. So what happens when they're next to each other?
You're dividing them.
What happens when they're next to each other? You multiply them. And yes, the factors do cancel each other out. You're just left with grams, and that's what we were looking for. Okay. Yes?
Are we gonna write these in scientific notation?
You.
Like, how would you do that?
Oh, this one here?
Well,
It's not for like, it's like bigger numbers.
Yes, you don't always have to use. If you're going into the millions, yeah, even tens of thousands, then you might use scientific notation. All right? Just out of curiosity, what would this be in scientific notation?
4.16 times 10 to the third.
Okay? Where do we get 1/6 though?
I meant 60.
Okay. All right. I just wanted to make sure I'm hearing you correct.
No, yeah, that's my bad.
You could have said you need to turn your hearing up.
I just wrote 1 kilogram on the things.
Okay. No, that's fine. We're doing okay. Okay. Yes.
What's the one with the lowercase d and the g and the lowercase c and the g?
Okay. This is decagrams. That's decigrams, centigrams, and then milligrams.
what would be,
How do you spell the D, the capital DG?
I think it would be something like, this is what I'm going with. Is that correct? It could be CK, it could be just C, but I think.
I don't know, I just wrote it down either way.
And
I just
then-
want the pronunciation correct.
Yeah. Oops. Oh, darn it. Gram. There we go. Okay. Can we close the door on this?
You said centigram?
Centigram. All right. Molar mass. That's what we're referring to on any substance or element that comes off of the periodic table. Is that a molar mass? I think these are maybe a little easier to read. Go ahead and take a look. It doesn't matter which table you use. Okay, I think there's 4 there. Yes? Yes? Just go ahead and we're back. Okay, so remind me if you're missing today, make sure you show up and get one of these. All right, bottom of page 83, molar mass. An alternative definition of mole is the amount of substance that contains Avogadro's number of particles. Can you figure out the approximate mass of 1 mole of helium atoms? You know that a mole of carbon-12 atoms has exactly 12 grams, okay? So what that means is if you had 24 grams of carbon, how many moles would you have? 2. If you had 36, 3. And if you went all the way up to 96, you would have 6. Yes. Okay? And then, okay, where do we leave off with? The atomic mass of helium atom has 4 AMU. It just means atomic mass units. For our purposes, we're just going to say grams. So we have 4 grams when you take it off the periodic table, which is about 1/3 the mass of carbon-12. it follows the mole of helium. It follows that a mole of helium atoms will have about 1/3 mass of a mole of carbon-12 atoms. Thus, 1 mole of helium has a mass of 4 grams. Someone in the back row made that correlation yesterday about, was it oxygen or nitrogen saying that it is 14 times heavier? Someone said something along those lines. Or was it not the back row? No?
Definitely wasn't me.
Oh, okay. Well, it doesn't matter. Okay. The mass of 1 mole of a pure substance is called the molar mass. So that's why if we say, I'll usually use sulfur as an example. So find element 16. Okay? So element 16 is sulfur. If you had 32.07 grams of sulfur, keep that in mind with what we just read. The mass of 1 mole of a pure substance, in this case it's sulfur, is called the molar mass of that substance. So if you have 32 grams of sulfur, how many moles is that? 1. 1 mole.
One. It all is different. Like it's like
If it's a substance or an element, if it's equal to that substance's atomic mass, then that is 1 mole. That's why we say 32 for sulfur. Because if we said 32 for any other element like copper, if we had 32 grams of copper, that's going to be about half a mole of copper.
Yeah, so 1 mole for copper is 64.
Correct.
yeah.
So there are 2 moles of sulfur. in
They're
one
all
copper.
different.
So-
Like
1 mole.
1 mole is one of that element.
Okay?
The moles aren't always the same.
Correct. The moles are not always the same.
So 1 mole of platinum would be 195.
If that's the atomic mass, yes.
And then once you like double it, then it's
Yep,
two.
then it's
Yep.
2.
Then it's two.
Okay.
Everything.
Yeah.
Molar mass is usually written in units of grams per mole. The molar mass of an element is numerically equal to the atomic mass of the element in the atomic mass units. Or if it's a compound, is equal to the compound atomic mass units added together. Yes?
So you could say, like, ask us what is a mole of sulfur, 1 sulfur, and we could say 32.07.
Yeah, because that's the atomic mass of sulfur. Yep. Okay. The molar mass of an element is numerically equal to the atomic mass of the element. Oh, we just read that. For example, the molar mass of lithium is 6.94 grams per mole, while the molar mass of mercury is 200.59 grams per mole, rounding each value to 2 decimal places. The molar mass of an element contains 1 mole of atoms. For example, 4 grams of helium, 6.94 grams of lithium, and 200.59 grams of mercury all contain 1 mole of atoms. Or we had said earlier, 32.06 grams of sulfur would have 1 mole of atoms. Okay, so how do we convert these? When it comes to these problems, if you ever have any issue, you have the textbook to go back to as a reference. Or possibly when we get further down the line, if we're confused, the seniors could probably help you out in this if you choose to ask them. Okay, so I always say there's sample problems on there. I leave that up to your responsibility to read through them if you think that you need to. Otherwise, we're on page 85, and we'll go ahead and look at 1, 2, 3, or 4. Okay, number 3. It says, what is the mass in grams of 0.135 moles of the element sodium? Okay, so some things you need to know is what substance is it and what are we starting with? Okay, so 0.0135, right? 0.0135, and it was moles of sodium. Okay? And I'm willing to bet that somewhere out there, someone is doing this. you could look at that and say, well, you're not wrong. Technically, you're not wrong.
What's the NX? Sodium.
Hmm. But when you do this, if you're just looking at this, well then how do you know what to put here? You don't know what substance you're dealing with. So it's always a good idea to label what it is that you're doing. Okay? So now, with our dimensional analysis that we learned with our grams and kilograms, how do we cancel moles out in our second step? Okay? So yes, we put for every mole of this pure substance of sodium, how many grams of sodium would that be? You don't make it up,
Multiply that by the mass.
which is 23. So when you write these labels out as you go, you can say, oh, well, I know this factor cancels out this one. We're dealing with sodium, and I know sodium has an atomic mass of 23. So when you multiply these out, you should get 0.310. Is that what we got?
Wait, so you multiply 0.0135 by 22?
Yeah, 0.31.
Because these are next to each other. Do we multiply or divide? You multiply. If it's on the bottom, you would divide. Okay?
And that's the mass.
Great.
That is the mass in grams. So if you're starting with this counting unit of this many moles of this pure substance, okay? Well, how many grams of that sodium do you have? Well, it's only 0.31. All right? We will pick up with this tomorrow. Oh, front row, are we on the bus here?
Yeah.
Second row? Third row? Okay, so if we're having problems, look around, find someone to ask questions with, and chances are they'll be willing to help you. All right, so we will catch up to you next time.